Welcome back to the Deep Dive. This is the place where we take specialized knowledge and turn it into actionable insight.
Today, we're continuing our journey into a really unique professional resource.
We are. It's the Intelligent Transportation Systems Masterclass, Networking 103, which was created by AtkinsRealis specifically for the Florida Department of Transportation, or FDOT.
And this isn't just theory. This is the practical, hands-on knowledge that, keeps our infrastructure running.
Our mission today is pretty straightforward. We're climbing the ladder of connectivity. We're going to unpack the upper 5 layers of the OSI model. That's layers 3 through 7.
Right. And just a quick recap. Last time we covered the basics. Layer 1, the physical layer, is the actual wire, the fiber, the copper cable.
And layer 2, the data link layer, that was all about local delivery using that permanent physical MAC address on the network card.
Exactly. Local neighborhood stuff.
Okay, so now we shift from that local neighborhood to, I guess, the global scale. Let's unpack this. Starting with layer 3, the network layer, what's the biggest change here?
The single biggest difference is we're moving from local to wide area communication. Layer 3 is all about enabling devices on separate networks to talk to each other.
So this is routing.
This is routing across the internet, or in the FDOT context, across huge regional transportation networks.
And this is where we stop relying on that permanent MS address and start using a logical address, the IP address.
Precisely. The IP address, which is governed by TCP/IP, is configured by network admins. It lives in software, and it can change. It defines where you are on the big network.
As opposed to the MC address, which just defines who you are locally.
Right. A key insight here, especially for anyone in IT, is the protocol that Layer 3 enables for them.
You mean NTCIP?
Yes. The National Transportation Communications for IT's protocol. It's a standard that makes sure a new traffic signal from one company can actually talk to an old message sign from another.
It's all about interoperability.
It is. It means these devices have to be, network aware. They need the intelligence to process that IP address. It can't just be a simple switch.
That makes sense. Okay, so at layer 2, the data structure was a frame. What does layer 3 create?
Layer 3 creates a packet. And the packet holds the data plus the really critical source and destination IP addresses.
But it can't just jump on the wire by itself.
No. The NIC, back at Layer 2, has to wrap that Layer 3 packet inside a Layer 2 frame before it can be sent. It's like putting a letter into a local delivery envelope.
So if a layer 2 switch manages frames, then a layer 3 router manages the packets.
You've got it. And the router's job is totally different.
How should we think about that?
Think of it like international shipping.
Yeah.
Your local post office, that's Layer 2. They only care about the street address, the MSC address, to get the package on the right local truck.
Okay.
But the router, that's the massive international sorting facility. When it gets the package, it doesn't care about the local street address at all.
It's looking for the country, the big picture address.
The IP address. It looks at the destination IP and figures out the best next sorting facility, the next router, to send it to. It then repackages it for the next leg of the journey.
So that's why the IP address is the guidance system for the entire internet.
It is. And then, only when the packet gets to the final destination network, the last router on the path adds the destination's local MC address back on.
So the local switch can make that final delivery.
A perfect handoff from global IP navigation back to local MP delivery.
Okay, so now we know where the data is going thanks to layer 3. But we have a new problem. How do we send a huge file? That brings us to layer 4, the transport layer.
Right. Layer 4 is the logistics team. The problem is simple. Most data, like a high-res video feed, is way too big to fit in a single packet.
So layer 4 has to break it up.
It does, a process called segmentation. The sending computer divides all that data into smaller pieces called segments or datagrams.
And then the receiving computer has to put it all back together, reassembly.
And the genius part is how it does that. Embedded in each little segment is a sequencing number.
Ah, like a page number. Page 1 of 120.
Exactly like that. It tells the receiver two things: the total number of segments to expect and the correct order to put them back in. If segment 4 of 12 is missing, it knows.
And what's interesting for FDOT is that layer 4 decides if that data is guaranteed or, just fire and forget.
Absolutely. For a critical alert, layer 4 will use a reliable protocol. It makes the system wait until every single segment is confirmed before it logs the event.
Okay, so moving up from logistics, we get into the layers that manage the user experience. Layer 5, the session layer.
The session layer is basically the digital telephone operator. Its job is to open a connection, keep it stable, and then close it when you're done.
And you can have multiple sessions at once.
Of course, you have a browser open, email, maybe this deep dive playing. Those are all separate, active sessions. And layer 5 makes sure the data streams don't get mixed up.
The masterclass had a great practical example for this, using the netstat A command.
Right. If you type that into a command prompt, you can see all the active sessions your machine is managing. You'll see things like established or listening.
And you see those port numbers, right? Like an IP address, a colon, and then a number.
Yes, and it's really important to know these are virtual ports, not physical ports on a switch.
So if the IP address is the street address of an apartment building,
The virtual port number is the apartment number. It tells the computer exactly which application, your browser, your email client, that specific data is meant for.
that's a great analogy. Okay, next up is layer 6, the presentation layer, the translator. Why is this so important for something like a transportation system?
Because layer 6 handles data conversion, it's about making sure the data is in a usable format. And for iTests, that really means encoding and compression.
Like H.264 for video.
Exactly. An FDOT camera sends a huge raw video stream. Layer 6, on the camera's end, compresses it into H.264 to save bandwidth. It also handles encryption.
So it's the efficiency and security layer. It makes sure the video is small enough to travel the network and that the receiver knows how to uncompress it and display it correctly.
It's a translator for efficiency, security, and compatibility. All three.
And that brings us all the way to the top, layer 7, the application layer.
This is where we, the humans, interact. Layer 7 is the software itself. Your email client, your web browser, or for FDOT, the specialized control software in the Roadway Traffic Management Center, the RTMC.
And it relies on APIs, application programming interfaces, to work.
Right. The API is what makes an application network aware. It lets the RTMC software talk to the network layers below it to send and receive data. It's the gateway between the person and the network.
Let's tie it all together with that practical example from the source. A CCTV camera sending video to an RTMC server. Let's walk the data down the stack.
Okay, encapsulation. So an operator at the RTMC clicks a button to pan the camera left. That command starts at the top.
Layer 7, the application, sees that pan left command. Layer 6 immediately translates it into a compressed standard format.
Layer 5 opens and manages a stable session to send that command.
Layer 4 gets it, breaks it into tiny segments, and gives them sequence numbers.
Layer 3 adds the source and destination IP addresses to route it across the FDOT network.
And Layer 2 adds the local MSE address and, crucially, some error checking information, then puts it all in a frame.
Finally, Layer 1 turns it all into light pulses and sends it down the fiber optic cable.
And when it arrives at the camera, the whole process happens in reverse. De-encapsulation.
Exactly. Layer 2 strips the frame. Layer 3 checks the IP. Layer 4 reassembles the segments into the original command.
Then layers 5, 6, and 7 deliver that command, now fully decoded, to the camera's software, and the camera pans left.
A 7-step dance, all happening in milliseconds.
That process also leads to a really important question about reliability. I mean, what happens if some of that data gets corrupted on the way?
If even a single 0 or 1 gets flipped, the entire message is wrong.
So you need detection.
And that detection starts back at Layer 2 with something called the frame check sequence, or FCS. It's basically a mathematical checksum.
Okay.
The sending computer calculates a number based on the data and puts it in the trailer. The receiving computer does the exact same calculation if the numbers don't match.
It knows the data is bad.
Right.
It's like the kindergarten teacher counting the kids on the bus. If the count is off, you know there's a problem.
Perfect analogy. Layer 2 detects the error, but it's Layer 4 that decides if we care enough to ask for a redo. For most data, it will request a retransmission.
And this is a huge, but for IT it's live video, and voice can't do that.
They can't. They use real-time protocols. The system just can't afford the delay of stopping and asking for a lost packet to be resent. The moment is already passed.
So if a packet from a live traffic feed is lost, it's just gone. That's why you get skips or jitter or pixelation.
Right. The system prioritizes the flow of the next piece of data over fixing the past. It's a deliberate trade-off between reliability and speed.
Understanding that really changes how you look at a system design, doesn't it? It explains why some things need absolute perfection and others prioritize just keeping the stream alive.
It's the core of network design. And it leads to one last thought-provoking idea from the source material. It's about Layer 3 and Layer 4 efficiency. We talked about how a router can be configured to drop malicious packets during, say, a denial of service attack.
Right, as a defense mechanism.
But here's the catch. To know that a packet is malicious and needs to be dropped, the router still has to spend processing power to inspect it. It has to look at the IP address, the port number, the payload.
So even rejecting something takes work.
A lot of work.
Mm.
So here's the question. If every action, even rejection, consumes valuable computational resources on critical infrastructure, what's the next leap in technology that will let these networks identify and reject threats without having to spend that precious processing power just on inspection?
That's a fascinating problem. How do you know something is bad without looking at it? A huge challenge for the future of network security.
It really is.
Well, thank you for taking this deep dive with us. We hope you now feel fully equipped to trace that 7-step journey data takes from a screen down to a wire and back up again.
Next time, we'll build on this and move on to network topology and Ethernet protocols, continuing our exploration of this fantastic FDOT training material.
Until then, keep digging for that knowledge.